Okay, so here we go for today. What I want to do today, I'd like to, Cody, why don't you put that away? Yeah, I'd like to review a couple things we talked about on Friday. Here's my strategy for the next few assignments. Here's what I want to do. Chapter 6, we've already talked about some stuff that's reasonably important, but the most important stuff in Chapter 6, and the hardest stuff, I should say, comes in sections 6.4 and 6.5. So this is the part where you really gotta, if you really pay attention to this and you don't get behind on the assignments, I mean, do these things soon so you can get some practice with them, you'll be fine. 6.4 has to do with, it has to do with factoring polynomials. Remember what factoring is. Just 10-second review of the concept of factoring. We haven't talked about this in a little while. Remember that if you start with a polynomial and you break it down into pieces, that's factoring. If you break it apart into a product of smaller factors, that's a little bit harder. What's easier is what you've already done, starting with the pieces and multiplying them together to get the polynomial. Okay, that's expanding or multiplying. So we're going to focus on the factoring part today. Now the nice thing about this is, Chapter 6, Unit 5, is really easily organized in your mind. There's a way you can set this up that just makes sense. The way that the factoring patterns or the factoring strategies that we use just depend on the number of terms that you're factoring. Okay? So if we're factoring 2 terms, this is the stuff that we talked about last Friday. Do you remember what did we say that? What was our strategy for that? Do you remember that if we had 2 terms? It's been a little while. And you might remember the words. Maybe when I write these words, it'll start to ring a bell a little bit. This was the sum and difference patterns that I'm going to force you to memorize, and I should have probably done it already, but I just haven't gotten around to it yet. Sum and difference patterns. We'll review those in just a little bit. So that's how we factor 2-term polynomials. We also talked about how to factor 4-term polynomials. Now you remember that? We take the 4 terms, we break them into 2 blanks. What? Factor by what? No, maybe. That's always something we have to consider. But as a general strategy here, this is the factoring by grouping, right? And I can see we need a little review of this, and that's fine. The assignments, oh, by the way, I was going to say, the assignments, rather than make one big factoring assignment, I've chosen to break it up into 3 very, very small assignments that focus individually on each of these 3 strategies or techniques. Okay, I think that'll make it easier for you to manage. Okay, the one we haven't talked about yet that we're going to talk about today, 3 terms. The strategy we have for that is a quadratic form, and we'll get to that a little later. Okay, let's start at the beginning though. Let's start with 2 terms, the sum and difference patterns. Okay, remember we had these 4 patterns, 3 of which worked, right? 1 of which really didn't actually. Okay, what was our pattern? Think back here, see if you can tell me, what was our pattern for this first one? And what would we call that? How would we describe that pattern? Is it a sum or a difference? Sum of what? Squares. Yeah, okay, it's a sum of squares, isn't it? So what is our sum of squares pattern? A squared plus b squared factors into, that's the one that doesn't work. Exactly. So it factors into itself. It doesn't factor at all. That's the smallest, that's the most we can break it apart is the way it starts. So in other words, this one doesn't factor. Right? Okay, what about this next one? What would we call that one? Difference of squares. Difference because we're subtracting and we got squares, right? So difference of squares. Now, do you remember how that factors? Good. A minus b, a plus b. Either order, doesn't matter, right? Okay? Now the other 2, what would we call this? Sum of cubes and difference of cubes. Good. Now those 2 kind of go together, don't they? Those 2 Those were the bigger ones a little bit, but they followed the same kind of look. They had the same structure. They had a small linear factor times a bigger quadratic factor, right? Let's start with the sum of cubes. A cubed plus B cubed factors into, first of all, what linear factor? A plus B. Okay, now, what helped you remember that? What was the pattern that you saw there that told you it was A plus B? Just remember. Okay, you might remember what we talked about on Friday. We said that whatever, if it's a sum of cubes, then the first factor is going to be a sum. So if that's a plus, the first operation is a plus, right? Okay, what if it's a difference of cubes? What goes down here? Yeah, B A minus B. Okay, so the first operation matches sum or difference, depending on which pattern it is, right? Okay, now the second bigger quadratic factor. Remember, it's quadratic, meaning that the exponents add to 2 instead of 1. So we had an a squared term and a b squared term and an a to the 1, b to the 1 term. Right? Remember talking about this a little bit? Okay, so what's going to be the sign then? Let's look at this top pattern. A cubed plus b cubed, sum of cubes. We had a plus b times a squared minus. It alternates, doesn't it? If that's plus, that's minus. And the last one is always plus. Good. Okay, it's coming back a little bit. So the bottom one would be a minus b times a squared plus ab. Last one's plus. Good. Okay. Good. So let's do an example of one of these. How about if we try something like 64x cubed plus 27 plus 27. Okay, so now, what's our thinking on this? How many terms are there in that polynomial? What do you think, Jade? 2. So what's our strategy? 2 terms, sum or difference pattern, right? So then we just have to figure out which is the sum or difference pattern that could work, and then we'll just see if it actually does work. So which pattern are we going to see if we can make work here? Sum of cubes, because I've got an x cubed plus, right? So that the only pattern that could possibly fit would be sum of cubes. So then the question is just, does it actually work? Well, let's see. Can we write this as a cubed plus b cubed? What's b? Gonna have to be 3. Good, because 3 cubed is 27, right? So the 27 can be written as something cubed, and the something is a 3. What about the 64x cubed? Can we write something that we could cube and get back that whole first term? 4x, right? Because 4 cubed is 64, and x cubed is what? X cubed, yeah, trick question, right? So we know that when we distribute the exponent 3 to both parts, we're going to get our 64x cubed. So we got it. We got our a, we got our b. We're just going to follow this pattern right there, right? Okay, so what do we get then? A plus b is going to look like what for us? 4x, because that's our a, plus 3, because that's our b. Good. Okay, times, what is a squared going to look like?
16.
Okay, and you got that because a is 4x, and we have to square the whole thing, right? Okay, a is the whole 4x, and we got to square a. Minus a times b, what's that going to look like? Plus b squared, which is just 3 squared. Now all we have to do is just simplify, right? So we get our 4x plus 3. Noah already told us that 4x quantity squared, if I distribute the 2 to both parts, I'm going to get a 4 squared, which is a 16 times our x squared, right? 4x times 3 is 12x, so I'm going to subtract 12x up there, and then plus 9. Okay. Now when we factor, we always factor completely until we can't factor anymore. So the other question that crops up here is then, this guy's done, isn't it? First factor is done because it's linear. In other words, the x is to the first power. And there is nothing I can undistribute for both parts, both terms. Right? There's no greatest common factor. So this one is definitely done. Okay. What about this one? Can we factor more?
No.
And the answer is a big fat no. We can't. Okay, and why is it a big fat no? Because it's always a big fat no with these kinds of factoring patterns. Okay? In other words, whenever we use a sum of cubes or a difference of cubes, the quadratic part that we get left over will never go any further. It's always an irreducible quadratic. You can try as you might, but you'll never break it down any further. Okay? That's good. It makes things a little bit easier, doesn't it? Okay, let's try another one of those. Maybe. Actually, we won't. If we have time. I think you're going to be fine with those. What about this? Okay, now this is one. How many terms? 4. Okay, so 4 terms. We said we factored what using what strategy?
The divide and conquer strategy.
Divide and conquer strategy. No. We said we're going to factor by grouping, right? Okay, but before we jump into some big fancy strategy, we always try to trim things down and make things as simple as possible at the beginning. How do we do that? Okay, I could factor a 3 out in this case, right? I could factor out a greatest common factor, which would be a 3. I could undistribute a 3. If I undistribute a 3 from each of those 4 terms, what am I left with? First term would be what? X cubed, right? Because 3 times x cubed is 3x cubed. Second one would be what? Good? Everybody sees that? Because 3 times negative 2x squared is negative 6x squared. Okay, next one. 4x, how about? Okay, last one. 8. Okay, all right, so what do we do? Okay, so that helped a little bit. That counts as factoring. We factored out this little itsy-bitsy constant factor, 3, but it did make the other part simpler. But we're still stuck with 4 terms in the other part, aren't we? Our strategy for 4 terms is grouping. So we have to take those 4 terms and we're going to group them into 2 groups of 2. So it's going to look like 3 times, first group is just the first 2 terms, x cubed minus 2x squared, plus the second group, which is a negative 4x plus 8. Okay? All right, now we got to get down to the strategy of factoring by grouping, which you have done. We did this, remember, well, we did it on Friday, but we also did this in chapter 5 when we did the A times B then split, A times C then split B strategy, right? Okay, so what do I do? How do I proceed with this factoring by grouping stuff? So we've got the 3 taken care of. He's done. But we're continuing inside these brackets to factor by grouping. What does that mean? What do I do to the first group? Here's my hint. What do I mean by that? What am I going to try to do to those first 2 terms in the first group? See if you can use the right math words too. Not isolate so much. Isolate's what we do when we solve or something. Right? We have an equation. What is it?
Breaking back to the simplest terms.
Okay, simplest factors. Yeah. You can try to break it apart. But how can I factor that? What can I do to those two? We always want to see if I can strip something away to make it simpler, right? Well, I mean, that's a good math word. I'm going to factor out the greatest common factor. See what's the biggest thing I can undistribute. So what is it? X squared. Now, I gotta look for the number part and the variable part. Well, there isn't a number. I only have a 1 as my coefficient of x cubed, so I can't take any number out. But I could take out a power of x. The biggest power of x that I could undistribute from both of those would be that x squared, because that's all that that term has to give away, right? So I can undistribute or factor out an x squared, leaving what behind? So this is my leftover factor. So x minus 2 is the leftover, right? Okay, now you might remember, and this goes all the way back to chapter 5 with the A times C then split B stuff, but also we reviewed this on Friday. We have to do the same process to the second factor, but or the second group, but it's a lot easier. It's a lot easier because we know that when this one breaks apart, one of those two things has to always be the same as it is in the first group. Which one?
The blue.
The blue one. Yeah, the leftover, whatever leftover I get here from the first group, my next move is to write that for my leftover in the second group. And then the question is just to find out, does that work? Right? Does it work? Here's how I do this. I always say, well, let's see. What would I have to distribute to the x to get a negative 4x?
Negative 4.
Negative 4. So the question is then, does it work for the other term also?
Yes.
Negative 4 times negative 2 is positive 8. Check. It works. Okay, so the pattern worked, right? Now what? Now here's the last step. You can't lose, you got to hang with me here for a second, because this last step is another one that people sometimes have a little issue with. Okay, so now I've got this broken, I've got the two groups broken apart into different greatest common factors, but the same leftover factors. So I could once again undistribute a common factor, the blue one, right? The blue one is a factor that's the same in both groups. It's being multiplied by x squared in the first group. It's being multiplied by negative 4 in the second group, but it's the same thing that's being multiplied. So I could undistribute that out front with the 3. Pull it out front with the 3, and then I'm left with my 3 times an x minus 2 times what? What's left behind when I factor out the blue factors? X squared plus negative 4, which is just x squared minus 4. Okay? Thus ends the grouping, factoring by grouping portion of the problem. We broke it apart by grouping into those three, well, it's two things, the blue and the red, right? Okay, now the question is, can we go any further? Well, let's see what's done. The 3 is done, right? Is the x minus 2 done? Can I break that apart anymore? No, I can't. That x is to the first power. I'm done, right? But this is squared. This is quadratic. Can I go further with that one? If I could factor this even more, how many terms are in it right now?
2.
So to go further with 2 terms, how do I factor 2 terms?
A plus B and A minus B.
Okay, it's going to have to be, it's going to have to be one of my patterns, isn't it? Which pattern would fit? Yes.
Why don't you just square root it?
Okay, good question, because I can't. What would be the square root?
There's an x squared, so that would be x minus 2.
Okay, but what that's, okay, now, if that were true, what that would be implying is this. If I said that the square root of x squared minus 4 equals x minus 2, then doesn't that also mean that x minus 2 squared would be x squared minus 4? Right? But that's not true, is it? X minus 2 squared is equal to x minus 2 times x minus 2, which I have to FOIL out, right? Okay, so that's not that simple, unfortunately. It doesn't work that way. Okay, so once again, let me ask you. Oh, went way too far. Okay, so which pattern then am I going to rely on here?
Sum of squared.
Sum of squares?
Difference.
Difference of squares. Good. This is the one I want right there, isn't it? Okay. A squared minus b squared equals a minus b times a plus b, or vice versa. It doesn't matter which order those factors. So X squared minus 4 is like x squared minus what squared? 2 squared. So that breaks apart into what?
X plus 2 and then x minus 2.
Good. And so our final answer just looks like 3 times x minus 2 times x plus 2 times x minus 2. That's completely factored. Is it written in its simplest form?
No.
It's a tricky one, isn't it? What could I do to make that answer just a little bit simpler? Here, I'll give you a hint. This might help if I write it this way. I'll write the products in a little bit different order. What's x minus 2 times x minus 2?
X minus 2
Squared. Yeah. So the easiest way, the most simplified way to write this would be 3 times x plus 2 times x minus 2 squared. Now, these can go in either order. Doesn't matter. But you do want the 3 out front. You always want to put the constant factor first. Okay, that's completely factored. Okay? Make sense? Okay, let's try one more of those. What about that one? How many terms? 4. So is there a greatest common factor I can undistribute? Not this time, is there? Okay. 4 terms, so what's my strategy?
Divide.
AKA grouping. Good. Okay, so we could do first group, x to the 4th plus 2x cubed plus negative 8x minus 16. Notice you got to put that plus sign between the groups. People tend to forget that. I don't know why, but people do. So first group. Start with the first group. What do I do? Undistribute the greatest common factor, which here would be what?
X cubed.
X cubed. Everybody see that? I could undistribute an x cubed, leaving me with what?
X plus 2.
Good. X plus 2. Plus. What do I write next? Cody, what's next?
8x, or distribute the.
Okay, I think you're onto something, but what do we always write next? We know that, which part has to be the same in those two groups? The blue or the red? The blue. So if this is an x plus 2, right, if the leftover in the first group is an x plus 2, we have to have the same leftover in the second group. Okay, does it work? What would have to go in here to make that happen?
Negative 8.
Negative 8. Right? And that works, doesn't it? Okay? So then, factoring by grouping, what's the last step? What does this break up into? The product of what two factors? X plus 2, right? Because that's the common factor that I can undistribute, leaving me with what?
X cubed minus 8.
Good. Okay. Now we're done with factoring by grouping, but we may not be done factoring total. We've broken apart. Look what we did too. We took 1/4 degree polynomial and we broke it up into 2 smaller ones. The blue one is done. Is the red one done?
No.
Okay, what's the only pattern it could fit?
The difference of cubed.
Difference of cubes. So then it would be x cubed minus what cubed? 8 is what cubed? 2 cubed, isn't it? Good. Okay, so we could write this as x cubed minus 2 cubed. And then this equals, we've got our x plus 2, which is done. Now, how does that factor? It's a difference of cubes. See if you can get this one right. How's that going to break apart? What's my a and what's my b?
Your A is X.
A is x, b is 2. Good. So then a cubed minus b cubed factors into a, what? What's the first operation going to be here?
Plus.
Which one?
Minus.
Okay, yeah, and it's minus because it's the same as this one, right? So it's x minus 2 times, what?
X squared
Good. A squared is like x squared this time.
plus
Plus
2x.
x times 2 is 2x, right? Plus a times b. Plus,
4.
yeah, 2 squared plus b squared is 2 squared, which is 4. Does this go any further?
No.
No. Big fat no, right?
Never, ever, ever.
That one never goes further, so we got it factored. Okay, good. Good. Okay. Okay, last example. Let's look at one like
That's 3.
oh, I have to do that. Let's do this. Okay, so let's go back and review some stuff from chapter 5. So what if we had something like this? What if we had x squared plus x minus 2? Okay, is that a quadratic expression?
Yes.
Just in case you want to, yeah, I can't stay awake, I understand. Try it. Somebody gets that, try it. So what, is that quadratic?
Yeah.
It is, yeah. Why is it quadratic?
Because that's 3 terms.
It has 3 terms, good.
Plus
Okay, good, and really think about it, it's just a times something squared plus b times something to the 1 plus c, right? What's my a?
X.
No,
1.
1. So the coefficient of x squared is a, so that's 1. What's b?
1.
1. What's c?
-2.
-2. That's all it takes to be quadratic. It has to fit the form a times something squared plus b times something to the 1 plus c. And the something has to be the same, right? Okay, so does this factor? Remember what we said, if a is equal to 1, it's easy to factor a quadratic pattern, right? Then we just have to find magic numbers that multiply to what?
They multiply to x, but add to.
Well, the
Add to x.
that multiply to c, but add to b, right? Okay, so what are those numbers here? What numbers multiply to -2 but add to 1?
X -1.
Yeah, so -1 and +2 I'm hearing, right? And then those are the magic numbers, 2 and -1. And in the binomial, whatever is the something that's being squared in the first term and taken to the 1 in the second term, well, that's the something that gets paired with the magic numbers, right? Agree? So that is quadratic, isn't it? Okay, what about this one? Is this quadratic? I didn't even ask if it factors. I just want to know, is it quadratic?
Yeah.
Yes.
Yeah, what's A?
At 1.
What's B?
-9.
What's C?
20.
What's the something that's being squared in the first term and taken to the first power in the second term?
X.
X, right? Okay, is it still quadratic if I do this?
Yeah.
Okay, what's A?
1.
What's B?
-9.
What's C?
20.
What's the something?
Y.
Okay, so it's quadratic, it's a quadratic pattern for A is 1, B is -9, C is 20, and the variable, or the something, is quadratic for y's this time, right? For the variable y. Okay, and that one also does factor. Okay, is that quadratic?
No.
Doesn't look like it, does it?
No.
Because it's not quadratic. It does look like it has an A and a B and a C, doesn't it?
Yeah.
What's A?
1.
What's B?
1.
What's C?
-2.
Okay, but there's not something squared and something to the 1 there, right?
Yeah.
Could there be though?
No.
What would it be?
X squared minus 2.
Okay, yeah. Now, the question here is just, could I rewrite this? If it's quadratic, it has to be a, which is 1 in this case, times something squared, plus b, which is 1, times something to the 1, plus c, which is -2. Could we fit something in there that would make that quadratic?
Oh gosh.
What is it again? X to the 4th is what squared? X squared, isn't it?
X squared squared?
Yeah. So this first term, I could just write as x squared squared. The second term I could write as x squared to the 1, couldn't I? Now that matches a quadratic form, because I've got a times something squared plus b times something to the 1 plus c, where a is 1, b is 1, c is -2. If it fits a quadratic form, then it also factors like any other quadratic. It would factor into, are there magic numbers that multiply to -2 and add to 1? You already did that one. What were they? Yeah, we got -1 and +2, but this time what's the something?
X.
Not x,
Oh, this one.
x squared. You see? So it is quadratic. It's quadratic not for x's, but for x squareds. Okay, but that still allows us to use all the same tricks that we had in chapter 5, right? So now we factored it. We broke it apart. The question now, and that helped a lot. We took a 4th degree polynomial, and we broke it into 2 small 2nd degree polynomials. Okay, can we go further? Does the first one go further?
Yes.
Okay, what pattern is 2 terms, so we got to look for a sum or difference pattern. What pattern would that be?
Squares.
Okay, well 1 is what squared?
1 squared.
Yeah, 1 squared is just 1. So that's like saying that's a squared minus b squared if a is x and b is 1, right?
Mm-hmm.
So that just breaks apart into what?
X plus 1 and X minus 1.
Very good. Okay, what about this one? No, does this one break apart?
No. Yes. No.
What pattern would that be?
The sum of.
Oh, it would be the sum of squares, which doesn't exist. So that one doesn't go any further. So we're stuck with the x squared plus 2, but now it's factored all the way. Right? You see it? See the trick?
So it's X squared plus 2 and then X. Oh, no, never mind. Keep going.
Yeah, just those 3 in any order you want. Okay? Okay, what about that one? Now this time we're solving an equation, right? Okay, so this, I wanted to include one today where why do we even factor? So these first assignments, they're just like when you're practicing, if you're practicing to be a good basketball player, you probably, like my son, he's got his super handles video. My 4th grade son's got a super handles video that he goes through every night in front of the TV with his basketballs to work on his ball game. When in the basketball game are you ever going to handle 2 basketballs at the same time? Never. Okay. In the course of a basketball game, you would never do that. But why does he do that? Well, because he's working extra hard on that skill, because that's an important skill for a basketball player. Well, along those lines, factoring is an important skill for a mathematician. So I'm going to make you guys do extra factoring. But why do we really factor? For this reason, to solve an equation, right? So let's do at least one of these where we're actually in the game now. We're not just practicing the drills. We're actually in the game and we're solving a polynomial equation. So the polynomial part of this on the left has how many terms? 3. So what's our strategy? Quadratic form. Okay, so can we write this as a times something squared plus b times something to the 1 plus c, in this case equals 0. What's a?
1.
1. What's b?
-7.
What's c?
12.
Okay, what's the something?
The X squared.
X squared, exactly. Okay, good. So this looks like 1 times something, which is an x squared, minus 7 times something to the 1, or something's an x squared, plus 12 equals 0. Okay, good. Now we got some options. If this were in chapter 5, what would you do in this situation if I gave you a quadratic equation? Well, how would you solve this quadratic equation? What if I said x squared minus 11x minus 13 equals 0?
The quadratic
You'd
equation.
use the quadratic formula, wouldn't you?
Yeah.
Okay? And that'd be fine to do. A is 1, B is negative 11, C is negative 13. That's all you need for the quadratic formula. The quadratic formula is equal to the something, which in this case is an x, right? So we get x equals negative b plus or minus square root b squared minus 4 times a times c all divided by 2a, right? Okay? And I'd be solving for x. Now, what if that was an x to the fourth and that was an x squared? Still quadratic. This part doesn't change, does it?
No.
What would be out here, though? What would our something be?
Square.
X squared, yeah. Okay, so we could do that here, couldn't we? We could use the quadratic formula, but hopefully it's easier. Can you sidestep the quadratic formula? Are there magic numbers that work? That multiply to 12 and add to negative 7?
4 and 3. Or 4 and negative 3. No, negative 4 and negative 3.
Negative 4 and negative 3, right? So our magic numbers here are negative 4 and negative 3. The something is an x squared, right? Those are the same numbers the quadratic formula would have given you, right? And so now the question is, okay, do we need to factor more? We could, couldn't we? We could take this first one and x squared minus 4, could I think of that as a difference of squares?
Mm-hmm.
What would 4 is what squared?
2.
2. So I could split this apart if I wanted to into what?
X plus 2 and then x minus 2.
Okay. What about this one? Is 3 a perfect square?
No.
So I'm kind of stuck with that one, aren't I? And then I could set all those equal to 0 and solve, right? Okay, did I need to do that? No. How come? If I'm just trying to solve the equation, I didn't really need to factor those. Why? Remember, when we're solving polynomial equations, we talked about this a little bit on Friday. All we have to do is break these things down to quadratic factors or smaller, and that's as far as we have to go is quadratic. Because at this point, I could apply the zero product property. I could say that the product of these two factors equals 0 either when the first one is 0, when x squared minus 4 equals 0, or the second one, x squared minus 3 equals 0. How would I solve that little mini equation there? X squared minus 4 equals 0.
Square root.
Good, I'd isolate x, because I can point to a single x, right? So I'd add 4 and square root. I get x squared equals 4, so x equals, be very careful, what?
2.
No,
8.
it's not just 2.
2i.
No. 2 or negative 2. Because remember, when I square root both sides of an equation, what do I always have to include? Plus or minus. So I get plus or minus 2. Okay? Did I need to factor it? No. I got the solutions more easily by just square rooting both sides, right? What about over here? Same thing, right?
Mm-hmm.
I would just set x squared minus 3 equal to 0, add 3 to both sides. And so what's x?
Plus minus square root.
Good. Plus or minus the square root of 3. So how many total solutions did I get?
4.
No, 4. Plus or minus, there's 2, and 2 more here. Plus 2 minus 2 plus the square root of 3 minus the square root of 3 for a total of 4. Okay? Make sense? Okay, so you got some short assignments to practice that. I think I'm going to take a roll here. You may just relax for the last couple minutes.